take dy by dx, then take d squared y by dx squared. Tell me what you get. So this time we'll be actually using some calculus. I hope you remember that it's a u by v function, isn't it? And the formula for that is, help me out, v du by dx minus u by dx by d squared. That is u, the whole thing will be here. So when you have a fraction like that, u by v function, that's the formula. Did anybody remember that? Okay. So that's what you have to use. So it's not going to be that easy. So you have to, this, what's the differential of this? It's a constant, so that's why it's put like that, so to make it a little bit easier. So the first term vanishes, and then the second term you have minus 2 times, take the differential of this with respect to x, which will give you, what's the differential of this with respect to x? The derivative of this with respect to x.
1 minus 3t squared. Is it just 1?
It's just 1, because t is a constant. You know, when you take, it's a partial differential.
So it'll be 0?
There'll be 1 here.
No, I know the t.
The t, yeah,
Yeah,
will be a
it's
0.
a constant, so it's a 0.
Correct. So you don't have to care about that. You know what I mean? When you take, how do you, I don't know how you guys read it. We read it as dou y by dou x when t is a constant. That means this is just 1, right? Continue. And then take the second differential. Take it and tell me what you get when you take the second one.
Why would you take the second one?
Just obey. If you, do you want to find the speed? Do you want to find the speed? Oh, you're thinking this is already the speed.
Yeah, that's what I said, right?
Neil, this is the speed of the particle. Do not forget that y is the displacement of the particle. You are asked to find the speed of the wave. You see that? No wonder you asked me why do you have to. Okay, dy by dx is the speed of the particle. We're not asked to find that. We're asked to find the speed at which the energy goes forward along the x-axis. The particles are going up and
How do you know the top of the wave, or two tops of the wave, one that has a particle?
doesn't matter. Whatever it is, the particles do not have the same speed as the wave. No. Because the particles keep on changing the speed. You see, particles have 0 speed at the amplitude. Right?
But isn't it the logic within a wave, the particle is moving in the same direction as the wave?
It is. But the particle goes back and forth again.
Oh.
But the wave continues. See the difference there? The wave continues. So the particle has a 0 velocity here at these 2 points. Wave continues. So both are completely different. Okay. Nice argument. Nice discussion. We need to have discussions here. Okay. So find dou squared y by dou x squared. Did anybody get it? Jason, you got it? Dou squared y by dou x squared?
Would it be 0?
No. No, because you would have this whole thing here. And then after that, I want you to go ahead of me. I want you to do dou y by dou t and dou square y by dou t. Yeah. First we take the partial derivative with respect to x. Next you take it with respect to time. That means x is a constant here, okay? In this case, t was a constant. In this case, x is a constant. Go ahead, do both. Otherwise, what's the use of saying, I know calculus? Now maybe, what is y? Maybe I should have told you that first.
What is one?
Yeah. What's the,
That's why it's realistic.
okay, what's the formula? I mean, what's the equation? That's what we started with this chapter with. It's simple harmonic motion. Y is equal to a sine, come on,
Yeah, it's minus omega t.
either kx minus omega t. Okay, that'll do, kx minus omega t. Right. So if you don't know that, you're not going to do anything. I should have told you that before. So, before we do this problem, we are trying to tackle it generally, okay? Then we'll, whatever results you get here, we're going to apply here. Otherwise, we'll have to do it each and every time, you know, with the function. So let's just take this, work with it, get a formula, and then we can apply to anything. Isn't that better? Rather than doing it with each and every function. So that's, get that. That's easy. That's easy to do because it's not a uv function or u by v function. Right? What is that? That is, sine would be cosine, and then you're talking about x. So you'll have to multiply with k, isn't it? And then take it the next time. Take it the next time. You're going to do that again. So you will get k squared. But this time it will be minus k squared, right? And then it will be back to sine. Look. Second, when you take, oh, I don't want to write it so you just copy it. That's what I'm trying not to do.
Are we going to do it both ways?
Yeah, then do dou y by, or it's called a linear wave function. Write that down. It's a linear wave function. That means a wave that moves along one axis, along the x, or along the y. So it's a linear wave function. Let us try to find the equation for a wave function. The equation for a linear wave function. Okay. So now for that, we remember that the wave function is written as y is equal to a sine kx minus omega t. It could be a cos kx minus omega t, it doesn't matter. But when you take the first derivative with x holding time constant, this is what you get, ka cos kx minus omega t. And then the second time you get minus k squared a sine kx minus omega t. Now do the same thing with time. Holding x constant, you will get minus omega a, that's minus because of the minus sign here, of course. And then you will get minus omega squared a sine kx minus omega t. Let's call this equation 1, that's equation 2, and okay, that's dou squared y by dou x squared. That was a mistake. Now, if you look at 1 and 2 and compare it, you can see that 1 by k squared, dou squared y by dou x squared is equal to 1 by omega squared dou squared y by dou t squared, because sine kx minus omega t is common on both, and the a too, so those will get cancelled. And then you can rearrange that to get k squared by omega squared. Just taking k squared to the other side. But remember that the velocity v is equal to omega by k. Therefore, you get it in this form. And that's the linear wave equation. On the left hand side you have dou squared y by dou x squared there, and on the right side you have the acceleration of the particle. And this is the wave speed. So that's a very important equation. The advantage of this equation is that if you are given any wave function, now we can find out the speed of the wave from that. Work with the other problem that I gave you and try to do the same. Try to take dou y by dou x and see, the idea is once you get this with the question that I've given you and you put it in this format, whatever you see here would be 1 over v squared is equal to whatever you get there. See that? From there you will be able to find the velocity. That's the idea.
So, dou squared, or dou y squared over dou x squared, what would that be
Now what is this? That's the acceleration of the particle,
on the particle?
isn't it? I mean, this is the acceleration of the particle. So, dou squared y by dou t squared. That's acceleration. Acceleration of the particle. What is this?
The acceleration of the wave?
Well, kind of. You cannot call it acceleration because it's not changing with time. You cannot call it acceleration. This is definitely the acceleration of the particle. So, in this equation, you're connecting the particle property with the wave property.
Is it like the ratio of the acceleration of the wave and the acceleration of the particle?
So this is not acceleration of the wave. That's what I'm trying to say. This is not. How can you call this acceleration? Because there's no time function there. This is just how y changes with x. You know what I'm saying? Look at it. There's more to it than you think. Look, if you take a snapshot of the wave, you have a particular y for a particular x, isn't it? Don't you? But in the next instant, what's going to happen to that y? Isn't it going to change? So the y changes both with time and with x. I mean, if you don't get that, you miss the whole chapter. Look, that's where the wave starts from. And let's say you're looking at a point here, x distance away from the origin. And you're looking at it at a particular time. Maybe at that time, the particle here is at that point. And remember, it's going up and down. But if you look at the same particle after t seconds, are you going to find that particle there? No. It would have changed its y, isn't it?
So it gives the position of the particle as a function of the displacement of the wave?
Yeah, is this the position of the particle? It relates the position of the particle as a function of the displacement from the origin. That equation. This is an example where you have to find the speed of the wave function. Let's say that y as a function of x and t is given by 2 by x minus 3t whole squared plus 1. So first what you would have to do is you have to take the first derivative of this function with respect to x, assuming t is a constant. And this is a u by v function, therefore the formula is going to be v du by dx minus u dv by dx whole divided by v squared. Keep that in mind as we do this. So in this case, v du by dx, now that's a constant, so it becomes 0, everything is gone, minus u, that's 2, and then the derivative of this, so that will be 2 times x minus 3t times 1. 2 times x minus 3t times 1, which I have not written, divided by the denominator squared, okay? When you take the second derivative, you're going to have to use the same formula, but this time it's v, and in this case you have to write the whole thing, that's v, and du by dx. So that's just going to be minus 4, because time is a constant, is gone, and you have x, so minus 4, taking this with respect to x. And then the second term would be minus u, which will be this thing, whole thing, dv by dx. And since this is already minus, the two negatives make a positive, and you are going to get plus 4 x minus 3t, and then the derivative of this term is, have to be careful with that, it's 2 times x minus 3t whole squared plus 1 times 2 times x minus 3t times 1, of course. So this can be, and the denominator will be whole raised to 2, which in this case is raised to 4 because the denominator is already raised to 2. And then, see, one of the terms there gets cancelled with the denominator, and therefore the denominator becomes whole cube. And the 16 you get because it's 4 times 2, 8 times 2, 16, and you can figure that out. And then it's simplified to 16 minus 4 is a 12 there. And you have the minus 4 because of minus 4 times 1. So that could be figured out if you look at it carefully. So once you've got dou squared y by dou x squared, we got to do dou y by dou t. So I'm writing the function again. And then dou y by dou t. Remember, x is a constant, so this time it'll be minus 2 times x minus 3t times minus 3. Because the first term is again 0, you get that. So when you multiply that, you get 12 because you have 3 times 2, 6 times 2, 12. And so when you take the second derivative, first write this whole term, which is what I'm doing now, so whole squared, and then take the derivative of the numerator, which is minus 36 because 12 times minus 3. And then minus, write the numerator as it is and take the derivative of this, which is 2 times x minus 3t whole squared plus 1. Again 2 times x minus 3t minus 3. There you will have to look at it carefully and use your knowledge of calculus to figure out how you get all these terms very carefully. And then simplify that. Plus 144 when you multiply all these, 12 times 2 times 2 times 3, and 2 negatives here, negative outside, negative here, make it positive. Okay, that's how you get 144, and then you can distribute that. You have 144 here and minus 36 here, so that gives you 108 x minus 3t whole squared, and then you have minus 36 because of this minus 36 times 1, and the denominator is unchanged. Now that can be written as 9 times because 9 is a common factor. So when you put it this way, and when you compare dou squared y by dou x squared with this, you see that dou squared y by dou x squared is 1 by 9 dou squared y by dou t squared. So, and comparing this with the general equation, which I can fly back to that general equation just for a second, and you can see that in the general equation you have 1 by v squared, dou squared y by dou x squared on one side. So when you do that, you get the velocity as 3 meters per second because this is the square of the velocity. So that's how you figure this out, and hopefully you've understood. Take a little bit of time to look at how the calculus part is done. Number 12 is real physics. Don't give up, because if it's not tough, it's not easy. I mean, it's not interesting. You want me to do problems like 1, 2, 3, 4 that we did? Man, it's so boring. And please correct, when I worked out the problem, I did it for the next minimum. In the last but one sentence, so that the next minimum is heard. Instead of maximum, just make it minimum. Did you correct that? By what distance should the microphone be moved parallel to the speakers so that the next minimum is heard? All right, can you sketch a diagram based on what's given there? The microphone is placed at a distance of 3.4 meters on the perpendicular bisector of a line joining two speakers that are separated by 3 meters. Can you draw a diagram? That's easy. Yeah. Speaker 1, speaker 2, line joining the 3-meter distance, isn't it? A and B. And the perpendicular bisector would be this line. And there is a microphone there. And is the distance given? 3.40. Okay. Now in this setup, would you hear a maximum here or a minimum? And what I'm going to tell you right now sweeps across like 3-4 chapters, the idea in this one. So better listen. Are these two distances equal? Therefore, you know that waves travel in the form of crests and troughs and so on. So if this is the source, you have crests here, you have troughs, crest, troughs. See, what I tried to do is actually a wave, going out in all directions. See? Waves go out in all directions, and I have tried to join the crests. I get a line, a solid line. And then when I join all the troughs, well, it's not perfect, but you know what I'm trying to do. You get a dotted line, and so on. And what is this distance? What is this distance? Wavelength. And so this distance is lambda by 2. From a crest to a trough is lambda by 2. Right? And if I have another source here, and then I have somebody listening up here, assuming it's sound, then if a crest reaches this guy from source B, surely a crest is going to reach the guy from A if both of them produce waves having the same wavelength. And if he's exactly like here. So two things. These two sources have to produce the same wavelength, and he must be exactly
The same distance.
but he need not be at the same distance. Now in this question it says, by what distance should the microphone be moved? Parallel to the speakers, in the sense, you can either move it that way, to the right or to the left, but you're moving this along this path. And so if you come here, let's say you come here, isn't it possible for the 7th crest, I'm just throwing in a number, the 7th crest to reach here, but the 6th crest to reach here? Because this distance is smaller than this, see? Isn't it possible? I mean, at a particular point, isn't that possible? Yes. Wouldn't you hear maximum again? Because it doesn't matter whether it's the 6th crest or the 8th crest, who cares? As long as it's a crest and a crest, you hear maximum. Got it? Is that clear enough?
Would you get that if you use the intervals of the wavelength over?
Yeah. So that means this distance must be lambda. Correct. If it was a maximum.
Or intervals of
If it's a minimum, see, I changed it to minimum, didn't I? We corrected it. Therefore, it should be lambda by
2.
yeah. So basically, you're asked to find out what's lambda by 2. That's the question. So from the setup, geometrically, can you find lambda by 2? Go ahead. That again would take some time, but are you able to follow what I, did you understand my explanation up to this point? Then we can save a lot of time. Okay? That's why I'm using all these tools, so I don't have to just waste a lot of time. I don't want you to get it all in one go, so. Okay. Take a look at this and try to understand. Again, this will be on YouTube. So, otherwise we'll never be able to do extra problems. Okay. That's what I was talking about. Let me complete the diagram. I'm sure everybody can find out S2 from there because 1.5 is half of 3, isn't it? And then is S2 equal to S1 in the first case? They are at equal distance, isn't it? So I got S2 as well as S1. And then the second case, I just put it as 1 and 2. I'm still calling it S2 and S1. Where did I get that 1.5 plus x from? I just call that x. That's all. So, because this is 1.5 and you've moved x, so now the distance is 1.5 plus x here, and here it's 1.5 minus x. So you see that you can split s2 squared minus s1 squared as s2 plus s1 times s2 minus s1, and this is what I've used there. Now when you open this term, you get 3 terms there, a squared plus 2ab plus b squared, as you can see, the same thing here, and then distribute the negative. So you get rid of all those terms or cancel out, and you just have 6x. But again, as I said, s2 minus s1 times s2 plus s1 is what you can write this as. So that's equal to 6x, and then rearrange to make s2 minus s1 the subject. Alright, now s2 plus s1 is definitely 3.71 times 2, which is 7.42. That's a little approximation there, but that's fine. And because we're dealing with real small distances. Because s2 minus s1 should be equal to lambda by 2. Why? Because in the problem you're asked to find the next position for which you get the minimum. So we are talking in terms of lambda by 2, and the wavelength is really small. That's why this approximation is okay, rather more than okay. And then the wavelength lambda is velocity by frequency, which I've written there, and then you have by 2, and so when you solve that you get 0.377 meter, which is equal to 6x, and so solve for x from there and you get it as 0.47 meter. So you'll have to move by about 47 centimeters to get the next minimum position. So that's how you work out this problem. Thank you.